This part, or the part covered in this set of slides on the third chapter, relates to the definition of resistance, thermal resistance. Thermal resistance are used extensively to approximate heat transfer through multi-layered wall in a simplified way. So it's a very nice, convenient tool to estimate how insulation layers or other layers in the structure do impact on the amount of heat that may be transferring from one region to another. So for example, if you're studying a particular closed system or open system and you want to figure out how much heat is going to be lost or gained through the closed boundaries, this is a very convenient tool. So I'm going back over definitions that were covered in second year in a very brief manner. Okay, so the first slide here defines the thermal resistance in the way we, in exactly the same way as we discussed in the previous video. Okay, so the thermal resistance is defined as the temperature difference across a one-dimensional structure divided by the rate of heat flow through that structure. Both delta T and Q are taken as being positive, following the convention we were discussing earlier on. So when you see the delta T and the Q, assume they are the positive value. You've determined the direction of heat flow prior to calculating the value of Q. If you want to relate the direction of heat flow, you would, in a conduction problem, you would refer to the X, Y, and Z components of the Q vector. So Qx, Qy, Qz. So the temperature difference in this case, if heat flows from the left to the right, would be T1 minus T2, because T2 is smaller than T1, therefore T1 minus T2 gives you a positive delta T. If you have two layers in series, and what we mean by that is that you put two layers, you stick them one next to the other, and the heat will flow through the first layer and then through the second layer. So what determines the heat, the rate of heat flow through the two, the properties of the two walls, and the temperature difference across the two walls. Okay, the temperature at the interface between the two will be a product of the other variables. Okay, it's not defined or predetermined. It will evolve as a function of either the wall properties or the temperature difference. How can we get a formula for the resistance to this multi-layer wall? Quite simply, you start from an exact equality, Ts1 minus Ts3. So you note that I referred back to the notation used in the formula sheets that's provided to you. Ts1 is temperature of the surface of the first layer, Ts2 is at the interface, then and between the two, and Ts3 is the third. So Ts1 minus Ts2 is exactly equal to Ts1 minus Ts2 plus Ts2 minus Ts3, because the minus Ts2 plus Ts2 cancel out. The reason we do that is because we can now use the definition of the resistance and use the value of Q in order to derive an alternative formula. That is this here, Ts1 minus Ts2, Ts1 minus Ts2, positive temperature difference. If you divide that by Q, you end up with R1. Okay, so Ts1 minus Ts2 is actually equal to Q times R1. If you bring the Q on the left there, you end up with delta T is equal to Q times R. So Q times R1. Then for the second layer, Ts2 minus Ts3 is equal to Q times R2. And you note that it's the same Q because the heat flows through the two layers in series. You cannot have a Q here, which is different from the Q here, because in that case, you wouldn't have a steady problem. And all these derivations are contingent on the assumption that you have a steady problem. Things don't change with time. There isn't that layer of sophistication in the resistance and definition of the resistance there. So we have QR1 plus QR2. You can factorize and you end up with Q times R1 plus R2. But what about the left-hand side? We define a new total resistance, which is essentially consistent with the definition of resistance, delta T divided by Q. So delta T would be equal to R of the combined two layers, so we call it the total R, multiplied by Q. So we have Q multiplied by the total R. If you simplify throughout the Q, divide throughout by Q, you end up with the definition of R total is R1 plus R2. That's it. It's just a definition. If you put two walls in series, each one having a resistance R, the first one having a resistance R1, the second one a resistance R2, the resistance of the combined two layers is R1 plus R2. You could, if you had three layers, it would be R1 plus R2 plus R3, and so on. You have different type of wall arrangements. One whereby you may have the wall with bottom half that's certain wall and the top half that's another wall, different properties of Q. So they would have different resistance. We still assume we have a one-dimensional problem in the sense that we're going to treat the effect of the combination of the two wall and calculate the total resistance. Assume we have a total resistance temperature difference across and Q. The formula will give us the way temperature varies throughout without taking account of the distinction between which layer you're in. You could if you wanted to, but that's not what we're going to do here. We're going to derive a total resistance that account for the combination of the two walls placed in parallel. Check if we have a visual representation of it, something like that. You have the top wall and the bottom wall. So forget about this for the moment. We're just talking about these two. So that's what this thermal network schematic diagram represents. And I have to talk about the schematic diagram now that I've mentioned it for the first time, but let's go on and see how we can derive a total resistance. We can't say now TS1 minus TS2 plus TS2 minus TS3. There is no TS2 and 3. There's no third temperature. Essentially, the left wall is exposed to, we assume, a uniform temperature. It's the same temperature, whether you're on the left of the top layer or the bottom layer. The right-hand side is exposed to the same uniform temperature there. So what we do know is that we have the same TS1 minus TS2 for the two. But more interesting is the fact that Q that goes into the wall, part of it will go through the top wall and the other part through the bottom wall. The total rate of heat flow through the wall will be the combination of the rate of heat flow through wall section 1 and some rate of heat transfer through wall section 2. So we have that equality. Q is equal to Q1 plus Q2. Q1 is equal to, if the heat flows from the left to the right, it means TS1 is greater than TS2. So you take TS1 minus TS2 to get a positive temperature difference, divided by R1 gives you Q1. So we rewrite Q, Q1, and Q2 in these ways there. So what is common in that case is no longer Q, but it's the temperature difference TS1 minus TS2. So you can cancel it out and you end up with an equality which relates R total to R1 and R2, but it's no longer R1 plus R2 that gives you R total, it's the inverse of R1 plus the inverse of R2 that gives you the inverse of R total. So that's the parallel arrangement definition of the total resistance. If you now have more than just conduction layer, but you have a convective layer on the left and a convective layer on the right-hand side, I'll discuss the reason for a change in profile there later on. We recognize the fact that the way temperature changes in a convective layer is different from what happens in the conduction layer. Okay, so let's not go into the details, but we know that that red curve here represents the variation in temperature as you progress along a line perpendicular to the wall, because no matter which line you pick, as long as it's perpendicular to the wall, you'll get the exact same temperature profile if you were right about your assumption that you have a one-dimensional heat transfer problem. So this is a multi-layer wall. So I'm now definitely going to introduce the principle of thermal networks. We've done that in second year. You know that essentially you have a temperature difference between 2 points along your X or your direction, your one-dimensional representation of space, so that line that goes in the X direction. We know that, well, if you have a temperature difference, it's because you've got a resistance to heat transfer. If you've zero resistance to heat transfer, it means even with a heat transfer taking place, if there is such a thing, then the temperature will be the same across the point. That's physically impossible, okay? While it is possible, it's extremely unusual. You will get a temperature difference because you've got a resistance to heat transfer. Okay? That's essentially, you need the temperature difference to drive heat flow, but the reason for the temperature difference is the existence of a resistance to heat transfer. So we represent that in that sketch diagram where we have a resistance and we use that symbol that's borrowed from electronics. You've got the resistance symbol, and across on both sides of the resistance, you've got a temperature on both sides, temperature T infinite 1, TS1. They are different because the resistance is non-zero. If you didn't have a resistance, you'd put just a straight line, and the two nodes would be at the same temperature. So anywhere along that straight line, the temperature is the same. We don't resolve changes in temperature, only across resistance. So what we do here is we say that as we travel along that one-dimensional domain, straight line, you will get temperature difference where resistance exists. Since there's temperature difference there, you need a resistance. There's temperature difference here, resistance, and so on. So you've got three layers there that induce temperature change. So you've got three resistance. The circle represents region of uniform temperature. So far away from the wall, we assume everything, the free stream is at the same temperature, T infinite 1. Here, far away from the wall, we assume the temperature is uniform in T infinite 2. So no matter where you go, if you continue, you still have the same temperature. At the interface between them, we decide, okay, let's try to find out the temperature there. And we define essentially the convective zone as essentially anywhere in between or anywhere that regional space that defines the temperature difference across which the temperature difference exists, where a resistance is essentially. So we've got our node, resistance, node, terminal node, show temperature node, resistance, temperature node, resistance. You've got three resistance for three layers and therefore four temperature nodes. The formula for resistance to convection is 1 over HA, and the resistance to conduction is L over KA. Where does that come from? Now let's go back to our tablets. You've got two laws, Fourier's law, conduction. We have Q is equal to delta T over R, and R in this case is equal, well, if you want to write it in non-vector notation, it would be K delta T over thickness of the wall, capital L, multiplied by the area of the surface through which heat is flowing. So if you've got your wall, perspective view, the thickness is L and the heat flows, so it's perpendicular. Okay, Q in this way. So Q is equal, and the area is the area of this face. R, therefore, is going to be, if you just manipulate these two, you end up with a definition for R, which L over Ka. Newton's law of convective cooling, Q is equal to H A multiplied by delta T, where you've got a surface at a temperature surface, the fluid at temperature infinite. If the heat flow goes from the surface to the fluid, it means Ts is greater than T infinite, and therefore in that case delta T is equal to Ts minus T infinite. You take the positive one. Since this is equal to delta T over R, then you end up with R is equal to 1 over HA. You can do the derivation yourself. And that's what we have here. 1 over HA for convection, L over AK for conduction, and 1 over HA for convection. The sum, the total resistance is sum of the individual ones. If you've got multi-layers, convection and conduction as shown here, you end up with slightly more complex, but the thermal network is the same. Then if you've got a more complex network where you've got parallel and in series, you can put your series and your two parallel. If you've got that, calculate first the total resistance of this one, and then the total of the three would be sum of this, sum of the total for this one, plus this one. This diagram exists if you assume that the temperature at the interface here is the same everywhere. And the temperature is the same everywhere there. Whereas this one is an alternative, and it's difficult, it depends on your heat flow, it depends on the conduction coefficient and so on. But you could assume that, in fact, okay, let's assume that the heat flows in parallel through here, and then heat flows in parallel through the whole thing. So we assume that the same temperature is over there, but you have a different temperature here to here, and here to here. Oops. So in that case, we divide in that parallel network, and you end up with the whole branch is parallel to this whole branch. We've reduced the area open by A over 2 here. We assume that the flow goes through there. Okay, so we've got two alternatives. The last one is one whereby you have to account for the fact that the area changes in a cylindrical coordinate system. So instead of working with your usual coordinate system, in that case, a Cartesian one, you can work with the cylindrical one, and we'll look later on in the context of a tutorial at the governing equations are different. That is, you end up with a resistance, even though it's conduction, which is different from the one that we just looked at, L divided by K divided by A. Okay, so the resistance has changed a little bit in Cartesian coordinate system. It's shown here through the conduction layer. The convection layer hasn't changed, but the area open to convection is larger here than here. Okay, so you end up with an area that's not the same depending on where you're positioning yourself. So very often you have to be a little bit more careful in that context. And there's a definition of the U value, which is quite similar to the resistance, but it's the inverse of it. And the U value doesn't involve the area. So I'll discuss all that later on. But what's important is that if you rely on the U value to do your calculation, remember that it's defined. It shouldn't be defined separately from the area when the area changes. So we'll come back to this notation later on. And that's the end of this first part of chapter 3. I'd forgotten just the one. Okay, so very briefly, we've got thermal resistance due to contact, and that thermal resistance is defined as a flux resistance. So instead of defining the resistance in terms of the rate of fluid flow, we define it in terms of the flux itself. Flux is defined as Q divided by A. So you can prove that the definition of the heat flux has, or the heat flux as unit of meter squared K by watt. So thermal resistance exists because you never have a perfect contact, as shown here. You've got cavity, you've got conduction contact, and we can't really resolve all that. So instead, generally, there's an experimental study that tells you for this type of surfaces, you can expect a thermal resistance or thermal contact resistance of that much, and you're given the value for R dash dash. So all I'm pointing out here is that all this data, most of it is actually summarized in the table in your formula sheet's first page, and we'll use it in the context of the tutorial.